The objective of this video is to practice using Ampere's law and Faraday's law, and to introduce magnetic equivalent circuits. So we're continuing our discussion of the application of Maxwell's equations to electric machines. And remember that the expectation is that you have a solid understanding of Maxwell's equations, but we're reviewing them because the way that we use them with electric machines may be different than how you've experienced them in your E&M course, your electricity and magnetism course. So with that in mind, let's start with considering an example of a toroidal core with a coil wrapped around it. And on this coil, I'm going to label the terminal voltage and the terminal current, direction or polarity. So I've labeled a V and an I, and I've indicated the direction of both. And then inside the core, I'm going to label the flux, the direction that we consider to be the positive direction for flux. And so you can see that we've used the right-hand rule, which is that if our current is going in the direction I've labeled here, it's going to tend to create a flux in the direction that I'm labeling with these arrows. And we'll assume that our toroidal core has a certain circular cross-section with an area of A. And so in this example, we're going to first use Ampere's law to calculate our magnetic field, our flux, our core flux, and our inductance of the coil. And to do this, we're going to make several simplifying assumptions. And you'll notice that this is going to be a trend in this class. Solving Maxwell's equations directly is nearly impossible. In fact, in a general sense, it is impossible. And so what we do is when we want to find analytic solutions, we make assumptions. And that's part of the experience of a machine designer, is knowing what assumptions are reasonable to make. In order to be a good engineer, you need to figure out what physics you need to include and what physics you can reasonably neglect in order to facilitate a problem that can actually be solved. So in this case, we're going to make the following assumptions. We're going to assume that fields are constant within the cross-section of the core. What does that mean? That means that if we look at the magnetic field over here and over here, we're going to have the same value because we're within one cross-section of the core. Next, we're going to assume that we have a mean path length that the field travels, and that mean path length we'll call Lm. So this hashed line that I drew here, this is our mean path length, our mean path around the magnetic circuit. And finally, we're going to assume that we have a constant mu r. That is, the relative permeability of our toroidal core does not vary as a function of the magnetic field that is carrying. If you'll recall in our previous video, we talked about how the magnetic permeability becomes a function of the magnetic field, that is, our cores saturate, and we sketched a BH curve. In this case, to simplify things, we're going to assume that we have a constant mu r. And if we assume that we have a constant mu r, that is, mu r is the same at all points in our core, that means that our field is also going to be the same at any point within our core. And we are also going to assume that we have no fringing flux. That is, at this point anyway, all of the field is perfectly contained within the core. No fringing and no leakage flux. And we'll talk about all these points as we solve the problem. So, our goal is to use Ampere's law to find the magnetic field, the flux in the core, and the inductance of our coil under these assumptions. So we can start out by writing Ampere's law in integral form. And so we're going to evaluate Ampere's law along the dashed line that is our mean path length. And you'll recall that from our previous video, we defined this quantity, the integral of h dot dl, as the MMF of our magnetic circuit. If we are evaluating Ampere's law along this dashed line, and we've said that we have a constant field along the entire length of the core, this integral becomes very simple. In fact, h is a constant value, so it comes directly out of the integral, and we can say that h times our mean path length is equal to this integral on the right-hand side. And this integral on the right-hand side is interpreted as the integral of the current density that passes through the surface which is enclosed by our line integral. So again, we've highlighted this orange path, this dashed line through our core. This closed path can be representative of the boundary of a surface. And so what we're saying here on the right-hand side of Ampere's law is that if we integrate the total current density that passes through that closed surface, so the total current density that's passing into the page, that is equal to our MMF. And if we look at the current density that passes through that closed surface, we zoom in on these conductors that are shown right here. This represents n turns of our coil. So we can resketch this diagram below, where we note that at each of these points here, we see current going into the page. And so when we evaluate the integral of j dot ds through this surface that goes into the page, we see that it encloses a total of n turns, each of which carry a current of I. And again, this is equal to our MMF. And we can now solve this for h. So I want you to notice, I'm no longer indicating that h is a vector. H was a vector here, but here h is not a vector. And the reason for this is that h dropped out of this integral up here because we assumed that it's constant at all points in the core. So we're now talking about it being a magnitude. But it does also have direction associated with it. It was constant at all points in the core along the direction of dl. So that means that if you were to pick a point in this, so say that you're interested in the h field right here, it's going to have the same direction as our mean path length. So it's going to have a direction like this. If you were to pick a point for h up here, it's going to have a direction like this. So if you're comparing the top and the bottom h fields, they have equal and opposite directions. In fact, h at any 180 degree change in location will have an opposite direction. So you have to interpret the quantity that you have here, h, based on the assumptions that you made when you solved it. Okay, great. We have an expression for our h field, but what we really want is an expression for b. That's what our goal is up here. And we get that simply by using our relation that b is equal to mu times h. So we've completed the first task that we were set upon. We found an expression for our b field. Next, we want to find an expression for the flux in our core. And since we've said that flux is equal to the integral of b dot ds, because remember, b is our flux density, it's like a current density, and if you integrate it over a surface, you get the total flux in that surface. Since we've said that b is constant over a cross-section of a core, that was our assumption over here, b can also come out of the integral. In fact, we can say that our flux is simply equal to b times our area, A. And we can plug in the value that we found for b and get this expression, where Ni, again, is simply our MMF. All right, so we've now found two of our three objectives. We found b and phi. Next, we need to find L. But before we do that, let's just take a second and reflect upon what we are seeing. There's an interesting analogy that's coming up. We can view this as electric circuit quantities. So I've already pointed out to you that flux is kind of like a current. It's the integral of our flux density over a surface. Current is the integral of our current density over a surface. So we can say that phi is similar to I. And we've already noted that MMF is similar to an EMF, or a voltage that we're applying across a path. So in an electric circuit, we're governed by Ohm's law, that V is equal to IR, or I is equal to V by R. In this case, we've got I on this left-hand side up here, so we've got phi, and we've got our voltage over here. And so we can talk about this quantity right here being analogous to 1 over resistance. And so what we do is we label this as a reluctance. We say that this quantity right here is a reluctance, which is analogous to a resistance, so that we can write out Ohm's law for a magnetic circuit as being so this ability to formulate a magnetic system as an equivalent circuit is an important tool and something that we will use throughout this class. As electrical engineers, solving circuits are our bread and butter. We understand the world through the perspective of an equivalent circuit diagram. And in a later video, we're going to build up how a series of magnetic components can be connected to form a complete magnetic equivalent circuit with reluctances as the elements in that circuit. But in today's lecture, we're just going to focus on the kind of fundamental basic components of this system. And the building block here is our reluctance, or which is analogous to our resistance. And so we can say reluctance is equal to the length of the element that we're considering divided by its permeability times its cross-sectional area. And this is again directly analogous to resistance, which is equal to a length of our current path divided by the conductivity of the material times the area. And the interesting thing about reluctance as compared to resistance is that in magnetic materials, our permeability is usually less than 10 to the 4 times that of air. While in electric systems, our conductivity, at least in copper, is typically 10 to the 20 times greater than that of air. And the consequence of this is that, well, we typically don't worry about current flowing outside of the traces of our circuit board. In a magnetic equivalent circuit, we do worry about flux traveling outside of the flux paths that we provide for it. So we like to pretend that all the flux is contained within this steel core, but in fact some of the flux will leave the core and travel in the air to complete its path. We'll come back to that at the end of this lecture. But right now, let's move on to inductance. And inductance is formally defined as being the flux linkage of a coil divided by the current required to create that flux linkage in the coil. And so in our case, we can talk about the flux linking our coil as being equal to the number of turns of our coil times the flux that's in our core. So that's to say that if we neglect the leakage flux, if we consider only the core, the flux that's flowing in the core, the total flux linkage of this coil is going to be phi in this path times the number of turns that the coil is wrapped around. And for completeness, we'll put a winding factor in front of this. And we've talked about winding factors a little bit already, and we'll get into it much more heavily in Chapter 2 of the textbook. But the idea of a winding factor is it's a way to account for derating the amount of flux that's linking a coil by how you've positioned the turns. And in this case, we've wound the turns so that they all link all the flux that's in the core. So in this case, Kw equals 1. So we can now solve for inductance. And if we relate this expression right here back up to our expression for MMF, we can see that this is simply equal to Kw times n squared divided by the reluctance of our core, which means that inductance is purely a geometric property. All of these terms are geometric terms. They have nothing to do with the amount of current that we're flowing. They have everything to do with how we position the coils that wrap around our core and the dimensions of our core, the number of times we wrap the coils around the core, and so on. And so we can see that inductance is a fundamental property of the design of our electric machine. And inductance is in units of Henry, which you should be familiar with from your prior coursework. So we've now completed all parts of this exercise. we found the magnetic field, we found the flux within the core, and we've found our inductance. Part 2 of the exercise is to use Faraday's law to find the voltage at the terminal of our coil. And when we do this, we're going to assume that we have no resistance in our coil, that our conductivity is infinitely high so that R equals 0. So take a look at this core. We've defined our voltage as having a positive terminal on the top where the current enters and a negative terminal on the bottom where the current returns. And we've defined our flux path as going clockwise around the core. And since we have no resistance, our voltage is going to be related to our back EMF. V is equal to plus or minus of our back EMF. Please take a moment to think about this. Is your terminal voltage going to be equal to the positive of your EMF? Or is your terminal voltage going to be equal to the negative of your EMF? Press pause now and press play when you are ready to resume. Alright, let's refer back up to this diagram. We had previously remarked that EMF is defined as, that the polarity of EMF is defined so to produce a current in a direction to oppose a change of field. And so if we assume that we have some kind of passive resistor connector here, or it could be a short circuit, what polarity would your EMF have to have in order to drive the current I? And in order to complete this path, we see that we would need to have a current going across our resistor like this. So our EMF would look like this. We'd have a voltage, an EMF source, that's pushing current through the resistor upwards and into the terminal to make the blue current path flow as indicated. And you can go back to our previous discussion about Faraday's law and validate that this matches our description of the flux linking the coil. So this means that our EMF is in opposition to how we've labeled our voltage. So V is equal to negative E, and therefore V is equal to our well-known and very familiar voltage equation for an inductor. So this is a nice and familiar result, but let's use it to make a broader point about sign conventions. It's interesting that the way we have chosen to label our voltage polarity in this inductor core disagrees with the way that we've derived our back EMF, or our EMF rather. So let's clarify why this happens and how we should choose to label the voltage polarity and current polarity. And it turns out that in electrical engineering we have two types of sign conventions. For passive components or electric motors, we use what's referred to as a passive sign convention. And in that case, current enters through the positive terminal of our circuit. And that means that V is going to be equal to a negative EMF. And that's what we have indicated up here in this figure. We can say that this is the passive or motor sign convention. That is what all of our blue labels are for V and I. And this is what you're used to seeing for inductors, capacitors, resistors. For active components, or generators, we reverse this. And in that case, voltage is equal to our back EMF, which is negative d psi dt. So I strongly suggest that you tuck this away somewhere safe. Of course, you're writing it in your notebook right now, but remember this one. This is going to come up frequently in your coursework and in your career if you're dealing with magnetic devices. And you'll need to be able to switch back and forth between these two sign conventions. So we're nearly done with this video. The last thing I want to discuss is this point that we made earlier about leakage and fringing fluxes. So as we've considered so far, we've said that we have no leakage or fringing fluxes, and we said that this meant that all field was contained within the core of our machine. And that's this gold flux path, this hash line that we've sketched around it. However, in real devices, as we've noted down here, in real devices, we're going to have some flux that's going to travel through the air because our relative permeability is just simply not that much better than air. And this is especially true if you introduce an air gap into your core. So if you have an air gap in your core, you've got a region in your main flux path where you have a high reluctance, and therefore more of your flux is going to be tempted to flow through the air. And so in actuality, if you do the FEA analysis of this core, you're going to see that you have some flux that will, of course, encircle your wires and not even enter the core. And we call this leakage flux. And likewise, you're going to have some flux that will be partially in your core and partially out. It won't encircle all turns. Maybe it'll encircle a couple turns, but not all of them. And this is also called leakage flux. And in this class, we'll be talking a lot about leakage or fringing fluxes, as well as the main or magnetizing flux. It's hard to depict the nuances of that in this simple structure, but keep your ears tuned for more discussions about leakage and fringing flux. In general, the main or magnetizing flux is the flux that goes where you want it to go. It links all turns of a coil. But the leakage or fringing fluxes are the flux that goes where you don't want it to go. It's partially in air in a region you didn't intend it to be, or it links only some turns of the coil, but not all turns of the coil. Alright, that concludes this video. In this video, we've practiced using Ampere's law and Faraday's law, and then we've introduced the fundamentals of magnetic equivalent circuits. We've talked about MMF and reluctance, and we've compared these components, MMF and reluctance and flux, to the electric circuit equivalent of current, voltage, and resistance. And this is something that we're going to build up more later and use as a tool in this class to study magnetic structures. So we have two pathways for studying the magnetic fields in our structures. One is, as we've discussed in this video, analytic derivations based on simplifying assumptions. So we make enough assumptions so that we can actually solve Maxwell's equations. However, this comes at the price of accuracy. We're also going to be solving the magnetic fields in the cross-section of our motors numerically using something called the finite element method. And that will be covered in a later video.